Welcome to the course on computer design of electrical machines. We will have a lecture 16 today on the topic design of single phase and induction machines part 1. So, this is the outline of presentation. It will start from applications of single phase induction motor, then construction and operating principle of single phase induction motor, then types of single phase induction motor, then of course it's a symmetrical component general model for the performance analysis and DQ modeling. Then we go single phase tangent analysis and followed by exercises and numerical problems and references. So, coming to introduction to the single phase induction motor, mostly small motors generally below 2 kilowatt induction machines have to operate with single phase AC power supply and that are readily available in homes and remote rural areas. So, however, for constant speed application, the most frequent situation, the induction motor are fed directly from the AC single phase power grid, and in this case we will call of course single phase induction motor. So, to be self-starting, as we know that single phase induction motor is not a self-starting. To make it self-starting, the single phase induction machine needs a travelling field at 0 speed, and this is in turn implies the presence of two windings in the stator, while the rotor has a extended squirrel cage. So, first winding is called the main winding, while the second winding either called auxiliary winding or normally or called starting winding, and which is in general called auxiliary winding. The single phase induction motor may run only either on main winding once they started, or they can run on two winding. So, thus except for low power around less than 1 by 4 kilowatt or quarter kilowatt, in general the auxiliary winding is active also during the running condition to improve the performance. Like now, coming to applications of the single phase, one of the very major applications where in India we are using around 3 crore induction motor, which are majorly out of 3.5 crore, 3 crores are manufactured every year using the ceiling fan for different kind of fan, especially like a domestic ceiling fan, as you can in the photograph, and how it is the internal winding structure, and the typically the stator inside and rotor is cage rotor, you can see it's normally put outside. So, this is something little different kind of construction to make for specific application of your ceiling fan. There are other kind of fan also using single phase induction motor, like a domestic pedestal or table fan. You can see how typically the stator core, unwound core is there, and as well as the your squirrel cage rotor is there, which have a spring, because single phase induction motor of course have a lot of space harmonics. So, that cause the many physical phenomena including the problem at starting, as well as the typically the phenomena typically under normal running condition due to space harmonics. So, to reduce that and to eliminate those effects like cogging, crawling and other physical phenomena, we normally use this skewing in this single phase induction motor. Then of course, we use in exhaust fan of different variety and different ratings, and you know what for we use normally exhaust fan in the typically either like in your kitchen or bathrooms, or as a some of the typically removing the gaseous kind of environment, just to reduce the kind of, you can call it the smell and pollution. Then we use desert cooler. In tropical countries like India, in summer we have a very high, you can call it let's say summer. So, to reduce the intensity of the heating, we use the desert cooler, of course with typically water flowing on the fins. So, we have a typically two motors in that, and both are single phase induction motor. One fan is the one motor is for water supply, which put on the fins, and other motor is mainly for typically runs as a fan. Then of course, we have a AC compressor you might have done, which use the normally capacitor, start capacitor and motor, two capacitor motors, because it needs a compressor needs a high starting torque as well as the running performance also. We want the optimum performance because it runs reasonably longer times. Like so, it needs high starting torque as well as you want good performance under running condition. The motor rating also reasonably little higher, around 1.5 kilowatt to 0.7 1 HP to HP, around typically order of that. Then we have a induction motor used in extruding for different kind of raw material. I mean, like as well as the cooling fan for typically for the DC motor. Then you use the kitchen centrifuge. Then you use in surface domestic single phase pressure pump. Like even many cases we use in case of hand suction pump, or we call it like a booster pump. Your rating is smaller, or we have a desert cooler pump as we have seen in desert cooler. I mean, normally shaded pole motor is huge, a very small rating motor, order of around 50 watt, and we have a refrigerator auxiliary fan motor also. Then we have a refrigerator compressor motor. I mean, for many applications, not only air compressor but for the even refrigerator, typically refrigeration, like a fridge or other kind of refrigerating system. Then the typical of 2 HP air conditioner rotary compressor for the refrigeration part, and typically air conditioner fan motor. So there are many, even in air conditioner also you have many motors. So these are also run by single phase supply, or normally as a single phase induction motor. Then your domestic vacuum cleaners, then room heater blower. And room heater have a heating element as well as you have a fan to have a circulation of, you can call it hot air. So for the purpose of blowing that, we use this single phase induction motor. Then you have a air blower motor. As you blow the air for typically for many purpose, either for cleaning or removing the dust in places where it is very difficult to go by otherwise, like so we use this air blower. So that's also have a single phase induction motor. Then we have a floor scrubber machine for the cleaning or planning. So that also we use typically single phase induction motor. Normally for all houses or buildings we have single phase supply. So this motor also run on single phase. Then we have of course a washing machine motor, which also single phase normally run. Then single phase motor for air purifier. Like then single phase, of course, food mixer, and then induction motor normally used in conveyor. Then induction motor used in electric shaver. Then typically 45 watt compressor for aquarium for running the water supply or circulation of water supply. Then of course diesel generator, small diesel generator, and machine tool, typically single phase induction generator, and then single phase servo motor, which are quite popular for many applications because it's a brushless servo motor. Then packing machine, food processing unit, pharmaceutical machinery, and bottle machinery of lower rating like 10 watt out of that. Then you have a plastic parasonic single phase motor. Then automobile air compressor using single phase induction motor. Induction motor in huge crushers. Then floor mill. Then you have a single phase motor, gear motor of to get a very low speed like 1 to 70 rpm and mild steel 120 rpm AC shaded pole motor, gear motor basically. So these are used for cooler, frost switch, refrigerator, exterior, medical equipment, display unit, and instruments fan. Then shaded pole motor for agitator motor, and then shaded pole C frame motor for refrigerator fan. Then large single phase induction motor typically for these are in general for like irrigation applications. They have developed typically for even reasonably large rating, about 50 horsepower single phase induction motor. So normally otherwise it is 0.35 half a horsepower to 5 horsepower worm producing with single phase induction motor. And then CNC machine lubricant tank single phase induction motor. Then tape recorder single shaded pole single phase induction motor. Then vintage established recording instrument tape recorder. Then swing machine spooler motor. Then your single phase for toys and stick item. As you can see, the shaded your squirrel cage rotor with the stator of typically with the stator winding in shaded pole. Then your induction motor used in concrete drilling machine. Then induction motor used in drilling machines. Induction motor used in industrial robots arm. Then induction motor used in palm oil extracting mills. Induction motor used in textile mill. And induction motor used for swing machine spooler motor. And this single motor used in electric motor driven pumping unit. Then conveyor driving motor. Then single phase induction motor used for less than typically 10 kilowatt for this conveyor kind of motor. And of course, these are application for wireless threaded pole motor, as you can see the how really the control is there for that. Then you have a oil discharge mechanism in rotor compressor. Then 25, of course, it's similar to like what you have single phase, like a single phase return pole motor, then single phase induction header with a proper controller. So now there are plenty of applications. We have seen more than 40-50 applications of single phase induction motor, which are normally you can call it dominating in domestic industry or domestic appliances and many other applications. I mean, you see day around life. Now we come to construction of single phase induction motor. So single phase motors are preferred over three phase motors for domestic commercial application, as single phase supply, only single phase supply is available from the utility, and these single phase motors are two phase. In true, they are normally in general two phase motors, and single phase induction motor is similar to three phase squirrel cage induction motor, except there is a single phase two winding instead of one three phase winding and three phase motors. So for the same output, a single phase motor is about 30% larger in frame size to a corresponding three phase motor. So you can just see typically how the photograph looks like. The main parts of this single phase induction motor are stator slotted magnetic structure, core, then stator electric winding. As you see here, rotor slotted magnetic core, rotor electric winding as a cage bar, and with the end ring, and stator frame and bearing and cooling system and thermal box. You can see an exploded view of the single phase induction motor with the squirrel cage. So with the side plate, then cooling fan, then you have a squirrel cage rotor, then you have typically the stator with the winding with thermal box, then you have another side cover with the cooling and the side cover. I mean, you can say the cutaway of this single phase induction motor, how it looks like a squirrel cage rotor with the SQ rotor bar with the proper ending, then stator core, typically cooling fan, then driving cooling arrangement, then bearing, a centrifugal switch, I mean for either capacitor start and capacitor start, capacitor run, because a capacitor which normally used for starting is supposed to come out during running condition. Like so, now coming to typical parts, like if we talk about stator laminations with the winding, so you can see how in photograph looks like your lamination. So stator core is same as the core of the three phase induction motor. In single phase motors, there are two windings are used in stator except the threaded pole induction motor. So stator core is laminated to reduce the eddy current losses. An iron core has a cylindrical shape and is laminated with the slots, and the iron core on the figure has copper liner insulation placed in some of the slots. So now coming to typically the winding. So there are two windings in single phase induction motor, main winding, or we also call running winding, as you can see in the diagram as well as in the photograph of the motor part, and then the actual stator winding is distributed in slot to produce approximately standard space distribution of flux. So you have a main winding and auxiliary winding here, as you can see. Then you have a rotor, the cage bar with the aluminum bars and end ring made of normally of aluminum with the skewing slot or skewing bar. The fan blades on top. I mean, these blades are also part of die casting of aluminum dash casting, which we do together. The rotor is not connected electrically to the supply, but has a current induced in it by transformer action from the stator. And most of the single phase induction motors use squirrel cage rotor. The copper bars and copper end rings are used in which the bars are brazed into the end rings. And a squirrel cage induction motor, the rotor bars conductors are screwed for quieter operation. Now coming to operating principle of this single phase induction motor. So the operation of single phase motor can be explained by two theories. One is forward backward MMF wave, another is Kurzweil theory. So coming to forward backward wave, the doubly revolving field approach decomposes a pulsating field into two counter rotating magnetic fields. So consider the equation especially sinusoidal distributed MMF with the pulsating MMF. So F theta t equal to F sine omega et into sine p by 2 theta m. So you can call it the forward and backward. So the product of cosine and sine function can be expressed in a manner that f theta t will be f by 2 cos in bracket p by 2 theta m minus omega t minus cos P by 2 theta plus omega t and the bracket closed. So in the above equation, the red section was P by 2 theta minus omega t is a forward counterclockwise rotating field sinusoidal distributed MF, and the blue section cos theta P by 2 theta plus omega t is a backward field rotating a sinusoidal distributed MF. So you can see the torque characteristic corresponding to that. The forward field is the red, which, and the backward field is the blue, and the net is your black. So you will just see at zero speed both are equal. So net torque produced is zero. Like typically, but you can see at any other speed, if speed is slightly higher, you can say the net torque increases because the forward torque produced by the forward field is more than the torque produced by backward field. So that clearly demonstrate or explain that once you start the motor by some means, it will go running, or it will certainly run and start in the forward direction and settle to a speed which is decided by the, of course, the load torque and proper slip with corresponding to this resultant torque. So this thing you can call it forward backward theory, can be used for analyzing the two field, typically forward field, backward field, and net torque of the two. So now coming to for this concept of this, as you can see here, we have a typically the you can say main winding and auxiliary winding, how really it is shown the diagram. So you can call it the interaction between the fields and the current induced in the rotor bar generate opposing torque. Under these conditions, with only the main field energized, the motor will not start. So however, if external torque move the rotor in any direction, the motor will begin to rotate, and single phase motor main winding generate a two field which opposes and counterbalance one another also. So now another theory, the cross field theory. So we consider, let's say, typically a cylindrical pole motor with a concentric single with a stainless steel rotor as shown in the figure. So here in cross field theory, the stator winding is excited by single phase supply. The supply produces alternating flux phi s, which acts along with the axis of the stator winding, and due to this flux, the EMF get induced in the rotor conductor due to the transformer action, and as the rotor close one, this EMF circulate the current through the rotor conductor, and direction of rotor current is shown in the figure. So direction of the rotor current is to oppose the cause producing it, which is stator flux phi s. So now Fleming left rule can be used to find out the direction of the force experienced by the rotor conductor. It can be seen that when phi s acts in upward direction, increasing positively, then the conductors on left experience the force from left to right, while the conductor on the experience from the typically experience the force from right to left. So overall, the force experienced by rotor is zero, hence the no torque exists on the rotor, and the rotor cannot start rotating. There must be two fluxes separated by the small angle to produce the rotating magnetic field, and according to cross field theory, the exterior flux can be resolved into two components which are mutually perpendicular. So one acts along with stator winding, another acts perpendicular to it. So if an initial push is given to the rotor anti-clockwise due to the rotation, the rotor physically cuts the stator flux and dynamically induced EMF get induced in the rotor. So there is a called speed induced EMF or rotational induced EMF. The direction of such EMF can be obtained by Fleming's right hand rule, and this EMF is in phase with the stator flux phi s, and direction of EMF is shown in the figure on next slide. As you can see how the flux, typically, so the induced EMF denoted as E2N, and this unit circulate the current through the rotor as I2N, and the current produces the flux called phi r, and the flux is at 90 degrees, so flux is stator, and this flux called the cross field like. So due to the very high rotor reactance, the rotor current I2N and phi r lags the rotational EMF by 90 degrees. So phi r is in quadrature with phi s in space and lags phi s by 90 degrees in the time phase. So such two fluxes produce the rotating magnetic field. So direction of this rotating magnetic field will be the same as the direction of initial push given. Thus the rotor experiences a torque in the same direction as that of rotating field, the direction of initial push. So rotor accelerates in the anti-clock direction under the case considered and attains the subsynchronous speed in the steady state. Now coming to, these are the two concepts which are used basically theory of single phase induction motor. Now we can certainly classify this single phase induction motor. So there are three main types of single phase induction motor are used in today in different applications. One is split phase induction motor, then capacitor induction motor, then serial pole induction motor. So coming to first is split phase. It has a two winding placed at 90 degree to each other, and the main winding has a low resistance and high inductance. As you see, in main winding is directly connected to the supply. The main winding is with the thick conductors having less number of turns than the starting winding, and main winding is embedded in the slot. So starting winding has more resistance and low inductance. So starting winding is kept with the thin conductor having more number of turns of some times equal. So now you can just see here the phasor diagram. Typically with respect to the voltage, you have a two current like IS current which have a small phase angle phi s, and another current IM of main winding current which have angle typically you can call it phi m, and the net current typically, the angle which you have here, it has typically the angle between the two currents which give it a theta, and you have another angle with respect to voltage and current, that's a perfect angle for the net resultant current. So the current of starting winding IS is near to the voltage vector because the higher resistance, and current of the main winding is towards lagging, that because of more inductance. The main winding is connected across the line, where the starting winding is only for the starting purpose, and starting winding is disconnected from the main winding by the centrifugal switch when the motor runs accelerate beyond 70% speed. There are two currents resulting two magnetic field which produce the magnetic field of rotating field in nature, hence the motor is start. And you can see the torque speed characteristic with the main auxiliary winding, and when your main winding cut, you run on the auxiliary winding, so you switch over to the torque speed characteristic is only with the main winding, as you can see in there. So starting torque is low, typically 100% to 175% of rated torque. The motor draws high starting current, approximately 700%, 7 to 10 times of rated current, and the maximum generated torque ranges 250 to 350% of rated torque. So good applications for split phase motor include the small grinder, small fan blower, and other low starting torque application with power needs of 120 to 1/3 horsepower, and avoid using this type of motor in application requiring high on-off cycle rates of high torque. So we have now capacitor start motor, where we have of course main winding, we have auxiliary winding. In series with we have a capacitor, and then we have a centrifugal switch which is responsible for opening this auxiliary winding with the capacitor after a certain speed, about 70% or so. So this capacitor is designed to have a phase shift at standstill or starting condition with the 90 degree from the main winding. So there are many criteria for designing this capacitor for purpose of starting. So disadvantage of the split phase motor is low torque production. The capacitor used in this motor is a dry type capacitor, and this is designed to use with the alternating current. So the starting torque of the motor is very high compared to the split phase induction motor. If the capacitor is in series with the start circuit, it creates more starting torque, typically 200 to 400% of the rated torque, and the starting current, usually 450 to 575 rated current, is much lower than the split phase due to the large wire in the starting circuit, and due to high starting torque. This motor is used in application where the high starting torque is required, like lathe machine, compressor, drilling machine, etc. So you can just see how really typically it works. So you have auxiliary current because of the capacitor, it leads by angle of phi a. Then you have another main winding current which lags by from voltage phi m, and then you have a net current. Angle between the two currents are typically general alpha here, but normally design sometime having a 90 degree, so that you have a 2 MF at 90 degree producing the two field. Exactly 90 degree as a two phase machine rotating field is produced as starting, and then you can see the torque characteristic with this capacitor and main winding auxiliary winding, a quite large torque around 350% of full load torque, and then it switch over around 75% speed because of centrifugal switch action, and then it switch over to only the single winding main winding only, with the other characteristic as shown here in the dotted line. So another is a permanent capacitor run motor. So many applications like fan, we use the capacitor permanently in the circuit of auxiliary winding. There is no centrifugal switch because we normally in those cases we design this capacitor only for running condition to give optimum performance under file running condition, but this capacitor is reasonably enough for providing a some starting torque which may be more than enough for some application like ceiling fan. So a permanent split capacitor motor has a run type capacitor permanently connected in series with the starting winding, and this makes the start winding an auxiliary winding once the motor reaches the running speed. Since the run capacitor must be designed for continuous use, it cannot provide the starting boost of a starting capacitor. So typically starting torque of phase starting motor is low from 30% to 150% of rated torque. The permanent capacitor single phase induction motor have low starting current and usually less than 200% of rated current, making them excellent for application with high on-off cycle rate. And permanent split capacitor motor have a wide variety of application including fan, blowers, low starting torque needs, and intermediate cycle use such as adjusting mechanism, gate operations, and garage door opener. So this motor, then we have a capacitor start capacitor on motor where we need a motor have to start type capacitor in series with the auxiliary winding like a capacitor start motor for high starting torque, and like phase PSC phase shifting capacitor, it also have a run capacitor that is in series with the auxiliary winding. After we start capacitor is switch off from the circuit, this allow higher overload torque, and this motor is costly due to start and run capacitor and centrifugal switch. You can just see clearly how this is. You have a two capacitor. One capacitor is a CR, that is running capacitor, and another is CS starting capacitor with a centrifugal switch. And of course, at the starting, we have a both capacitor connected are parallel, so net capacitor is equivalent to sum of the two capacitor, which is connected in series with the auxiliary winding. And of course, you have a main winding connected directly, and you can see the torque characteristic. First, it remains on a starting capacitor with producing high starting torque around 200%, and once it comes to 75% speed because of action of centrifugal switch, it switch over to another characteristic which is with the running capacitor and with the two windings like. But normally these motors are usually used for high rating order of 3 horsepower like 2.2 kilowatt motor or higher than that. Then another category motor is the like a saddle pole single phase induction motor. So saddle pole motor have only one winding and no start winding. So starting is my means of design of rings a continuous copper loop around the small portion of each of the motor stator pole, and this shaded portion of the pole causing the magnetic field in the shaded area to lag behind the field of unshaded typically portion. The reaction of the two fields get the shaft rotating, as you can see here in the diagram how the shading coil is put on the core and winding put on the other portion. So because the saddle pole motor lacks the starting winding, starting switch of capacitor, it is electrically simple and inexpensive. So the speed can be controlled namely by varying voltage or through multi tap winding. So you can just see the how the typically shading coil is put and how your winding is put, stator winding is put in this motor, and how simplified this motor is there typically like. So you can see torque characteristic is quite smooth, but of course your starting torque is low. So it has a low starting torque, typically 25 to 75% of rated torque, and it is a high slip motor with the running speed 7 to 10% below the synchronous speed. The generally efficiency of this motor is very low, order of 20%, and the low initial cost suits the saddle pole motor to low horsepower or light duty application. Now coming to equivalent circuit of the single phase induction motor. So we have a simplified equivalent circuit with the single winding, where we have a main winding resistance reactance, and we have a the forward branch and backward branch. Of course, it is similar to like a 3-phase induction motor, but divided by 2 under block rotor condition. But under running condition, of course, for forward field slip is 2 minus S, and forward field slip is S, and backward field it is 2 minus S. And when you really combine together, so you have all three impedance, your R1, X1, and then your forward resistance, backward, then reactance, then forward resistance and backward resistance. And you can find out the impedance for forward equivalent part and backward equivalent part. Then you have a three impedance as a total impedance, your Z1 stator impedance and forward and backward field, and you can find out the input current I1 V1 upon Z in, and the power of your real part of V1 I1 conjugate, that is V1 I1 cos phi, and stator couple loss is your I1 square R1. Then you can find out the forward branch current I2F from I1 JXM by R2 by S plus J R2 by X2, because by 2 is cancel out, and similarly current in the backward field I2B I1, except the difference is in this JXM divided by R2 by 2 minus S plus J X2 XM, and air gap power is of course your forward power AGF I2F square R2.5 by S, and your PAGB I2B R2.52 minus S, and net air gap power which is crossing the air gap from stator rotor is PAG PGF minus PGP. So you can call it the developed power PD is 1 minus S into PAG, and that is T into omega, and TD1 minus S into omega. So you can call it developed torque is your PAG upon omega, and power at the shaft will be PO PD minus PR, where rotation shaft torque is TS equal to P upon omega. Now coming to the typically equivalent circuit of the split phase capacitor motor. So you can say you have equivalent circuit for main winding with a similar to what we have with the single winding, and but we have another equivalent circuit with the auxiliary winding, where we are connecting capacitor in series with the stator winding. So that stator winding parameter are there, but the rotor parameters here, only the major difference is that you have a typically a square turns ratio in the equivalent circuit parameters like here. So you have it typically, but the supply voltage is the same to auxiliary winding in with the series capacitor here. So from this you can just do all the calculation. So other parameters of the auxiliary winding have been identified in terms of ratio. So the equivalent circuit of shown here strictly supply to permanent split capacitor motor, and capacitor impedance is replaced by minus JXC by a source circuit if we want to analyze the split phase motor. So for capacitor start, capacitor run motor minus JX had two different value, one for start capacitor, another for run capacitor. So for split phase motor we can call it Z equal to RA, and for capacitor start motor Z equal to RA minus JX CS, and capacitor start capacitor run motor it is J equal to RA minus JXCR. For phase permanent phase split capacitor motor Z equal to RA minus JXC. So now you can similarly find out the forward and backward impedance of main winding, ZF equal to RF plus JXF, and 0.5 JXM R2 by S plus JX2 divided by R2 by S plus JX2 plus XM, and similarly ZB equal to RB plus JXB, that is 0.5 JXM parallel to that R2 plus 2 minus S plus JX2 divided by 2 R2 by S minus 2 minus S plus JX2 plus XM, and the induced EMF in the main winding by this backward and forward EFM equal to I1 ZF and EBM I1 ZB. Similarly for induced EMF for auxiliary winding will be EFA equal to I2 A square ZF and E2B I2 A square ZB. So since the main winding is replaced by 90 degree ahead of the auxiliary winding, so induced EMF in the main winding by forward in midfield auxiliary must lag by 90 degree induced EMF in auxiliary. So in addition, the induced EMF in the main winding must be 1 by A times the induced EMF in auxiliary winding. So we can call it E1 will be equal to minus EFA by A, that is minus JAI2 ZF, and you can say simplified equivalent circuit where we are representing of course main winding impedance and the backward and forward field with their respective impedance, and then similarly for auxiliary winding circuit also another than Z where the capacitor is involved that impedance. So we have backward field forward as well as their forward back EMF and reverse back EMF. So by the same token, the induced EMF in the main winding by the backward field rotating side by auxiliary winding must be lead 90 degree. The induced EMF induces the auxiliary winding. So E2 equal to my J EB upon A, that is equal to JAI2 ZB. Similarly, the induced EMF in the forward and backward branches of the auxiliary winding by the forward and backward rotating field winding are E3 JI1 ZF and E4 minus JAI1 ZB. So since all the induced EMF are now known, the application of Kirchhoff's voltage law to couple circuit yields I1 multiplied R1 plus JX1 plus EFM plus EBM plus E1 plus E2 equal to V1, and I2 ZA plus JA square X1 plus EFA plus EFB plus E3 plus E4 equal to V1. So after substituting the induced EMF, we can express the above equation in concise form. I1 Z1 plus I2 Z12 equal to V1 and I1 Z21 plus I2 Z22 equal to V1. So I mean now we can say Z11 is where Z11 is your R1 plus ZF plus ZB plus JX1 and Z12 is minus A in bracket ZF minus ZB and Z21 again JA in bracket ZF minus ZB and Z22 is ZA plus A square ZF ZB plus ZB plus JX1. The current in the main auxiliary winding will be calculated from there. I1 equal to V1 in bracket Z22 minus Z12 divided by Z11 and Z22 minus Z1 Z and Z21 and I2 equal to V1 in bracket Z11 minus Z21 divided by Z11 Z22 minus Z12 Z21. And now line current is IL equal to I1 plus I2. And you can find out the power supply to the motor P in equal to real part of V1 IL conjugate, that is V1 IL cos theta, and where theta is the power factor angle between line current lacks the applied voltage, and stator copper loss for both winding is now PSCL equal to I1 square R1 plus I2 square R2 RA, and PGFM will be real part of PFM plus E1 to I1 conjugate, or real or equal to real I1 square minus J I1 conjugate I2 bracket and then ZF. Similarly, PJFA for auxiliary, it will be real part of PFA plus P3 I2 star, or equal to real part of I2 square A square plus JA I1 I2 conjugate into ZF. So you can find out the net air gap power. Typically, due to the both word field will be PJF equal to PGFM plus PGFA, and that is equal to I1 square plus I2 A square I2 square RF plus 2 A I1 I2 RF sin theta, where I1 equal to I1 theta 1 and I2 equal to I2 theta 2 and theta equal to theta 2 minus theta 1. So by the same token, the air gap power delivered by backward rotating field is PAGB equal to real part of EBM plus E2 I1 star plus I1 conjugate plus EBA plus E4 I2 conjugate, or that becomes equal to I1 square plus I2 A2 square I2 square in RB minus 2 A I1 I2 RB sin theta, and hence the net air gap power developed by the motor will be PAG equal to PAGF minus PJB, that is equal to I1 A square I1 square plus A square I2 square into RF minus IB plus 2A RF plus RB into I1 I2 sin theta. So now coming to equivalent circuit of single phase induction motor, so parameter estimation of equivalent circuit parameter, the method to determine the winding resistance of main winding and auxiliary winding are not discussed here, because we can use any method that accurately determine the resistance of these winding, and the other equivalent circuit parameter for single phase induction motor can be determined by performing block test, rotor test and rotor test on both the winding. So coming to first as a block rotor test, the block rotor test is performed with the rotor held stand still by exciting one winding at a time while other winding is left open, and test arrangement with auxiliary winding is open. And the test is performed by adjusting the applied voltage until the main winding carries rated current. Since the slip is at stand still is 1 in either direction unity, the rotor current impedance is usually much smaller than the magnetizing reactance. And you can see the circuit setup for making this test. Typically you have a voltmeter, ammeter and wattmeter for measuring voltage current when main winding is excited for block rotor test. So we can say how we really measure the parameter. If we consider the VBM, IBM and PBM are the measured parameter of voltage, applied voltage, main winding current and power supply to the motor under the block rotor condition. So magnitude of impedance will be ZBM equal to VBM upon IBM, and the total resistance of the circuit RBM will be PBM divided by IBM square, and not reactance will be XBM under root ZBM square minus RBM square, and RBM is equal to R1 plus R2 and XBM equal to X1 plus X2. So since the main winding reactance is already known, the resistance is known, so resistance of at standstill R2 can be RBM minus R1. To separate the leakage reactances of main winding and rotor, once we make the same assumption that we have that these are equal, X1 equal to approximately X2, that is 0.5 XPM. So now coming to like main winding open circuit test, we can also perform the block rotor by exciting auxiliary winding with the main winding, and let the PBA VBA and IBA be the power input, the applied voltage and current and auxiliary power when total resistance still. So resistance of auxiliary winding can be found out computer RBA equal to VBA IBA square, and R2BA will be RBA minus RA. So now we can now determine the A ratio, the ratio of effective turns in auxiliary winding to the main winding, by square root of the ratio of the rotor resistance as we from the auxiliary winding to value of rotor resistance as we from the main winding. Thus, so A equal to under root R2 upon R2. I mean the rotor resistance measured with respect to the auxiliary winding and main winding. So now coming to the node test with auxiliary winding open or exciting only main winding. So in fact we consider the rotor branch as open circuit because of the very low slip at no load. So in a single phase motor running on main winding, the no load slip is considered higher than the three phase induction motor. So still we assume that the slip under no load is almost zero. So replace the rotor circuit with the forward branch with the open circuit under no load, and even the error in introduced calculation of the parameter based on this hash is somehow greater than that thing. So making such assumption, however, does simplify the equivalent circuit of main winding under no load and auxiliary winding open. So we can say let the VNL, INL and PNL are the measured value of rated applied voltage, current and power intake by the motor. The load condition, then no load impedance is ZNL equal to VNL upon INL, and the equivalent resistance is RNL equal to PNL divided by INL square. And you can see the equivalent circuit how it is shown with the R1 and corresponding to S equal to 0. So hence the no load reactance will be XNL equal to under root ZNL square RNL square, and XNL will be X1 plus 0.5 XM plus 0.5 X2, or X, where X1 equal to X2 0.5 XPM, or you can call it X1 plus 0.5 X2 equal to 0.75 XPM, or XM equal to 2 XNL minus 1.5 XPM, and final rotational loss will be PR equal to PNL minus INL square in bracket R1 plus 0.25 R2. Now coming to after this measuring the parameter equivalent circuit of both the winding as well as single winding, we go to for now symmetrical component of a general model. So for steady state and sinusoidal current, time phasor may be used. So unsymmetrical MMF current and voltage correspond to the two winding of single phase induction motors may become composed in symmetrical system, which are in fact forward and backward component reduced in the previous slide. So it goes without saying that two winding are 90 degree, 8 degree phase shifted spectrally. As you can see here, auxiliary winding, main winding, not necessary to we have exactly 90 degree, and we have it typically with a different symmetrical component of two phase, where we can say A plus equal to minus J AM plus, and A minus is minus JM minus. I mean dividing this your unbalanced two phase into symmetrical component of the two phase. I mean like for positive sequence and negative sequence which have a different direction of rotation. You can clearly see in first case of forward A is leading than the M, and the second case of course A is leading the AM leading than the leading. So you can call it according to superpositional AM equal to AM plus AM minus, and AF equal to A plus AM minus. And using these equations we can call it AM plus is equal to half AM minus AA, and AM minus is half AM plus JAA equal to A conjugate AM plus. So now denoting VM plus, VM minus, IM plus, I minus, and respectively VA plus, VA minus, IA plus, IA minus, the negative voltage and current component of two winding circuit, we may write the equation for 250 sets to symmetrical machine whose traveling fields are opposite. So VM plus equal to Zm plus Im plus, and VM minus equal to Zm minus Zim minus, and VA plus equal to Za plus Ia plus, and VA minus equal to Za minus Ia minus, and VM equal to VM plus, you can call it VM plus 2 and plus minus, and VA equal to VA plus VA A minus. So Zm plus Zm minus are respectively Za plus and Za minus represent the resultant forward and backward distributed impedance of the fictitious induction machine per phase with the rotor cage circuit reduced to M and respectively stator winding. And you can just see these two clear current circuit where S plus is equal to H and S minus is 2 minus H in these two typically two circuit for, you can call it the typically for equivalent circuit for plus minus impedance reduced to main winding and reduced to auxiliary winding like with the notation. So when impedance ZA is connected in series with the auxiliary winding, then both winding are connected to power grid with the voltage Vs. So Vm equal to your Vs and Va plus Ia minus to Z equal to Vs. So it is generally more comfortable to reduce all the winding on the rotor and on the stator to main winding. And the reduction ratio of auxiliary to main winding is a coefficient of turns ratio. We call it A equal to N upon Nm into Kw upon Kw1. While winding is distributed, that's why not only simple number of turns, but we have to take the winding distribution also into account to decide the effective turns ratio. So the rotor circuit is symmetrical when A square XRM equal to XRA or A square RRM equal to RA. So currently we say delta XA equal to XA minus A square XSM equal to 0 or delta RA equal to RS equal to RSA minus A square RSM equal to 0. So voltage and current reduction formula from the auxiliary to main winding are VA dash equal to A upon A and IA dash equal to A into IA, because this dash quantity are referred to the typically main winding. And you can see the equivalent circuit how it is really referred to the main winding with the symmetrical components. You have a positive sequence and negative sequence of typically for rotor and stator, like with these impedance as it is explained there. So you can say average torque will be equal to T plus T minus and 2P1 upon omega 1 in bracket I Rm square RRM by S minus I Rm square RRM divided by 2 minus S. So for the case when auxiliary winding is open, Z equal to infinity, IRM equal to IRM minus. In such case, S equal to 1, start the torque is 0 as expected. Now coming to DQ model of the single phase induction motor. Here we consider the typically the main winding auxiliary at 90 degree and DQ axis of rotor winding also at similarly at recorded. So as the stator is powered with two orthogonal winding and the rotor is fully symmetric, the single phase induction motor is suitable for the direct application of DQ model in the stator coordinate. So rotor will be reduced here to main winding while the auxiliary winding is not reduced to main winding. So DQ model equation in stator coordinates are straightforward. So DQ model in stator coordinates we can say I am RSM minus VM equal to minus d phi m upon dt and IA RSM minus VA equal to minus d phi upon dt and IDR equal to minus d phi d upon dt minus omega RA psi A and IQ RR minus d phi A upon dt plus omega R phi d. So flux relationship here is a phi d, that the rotor flux will be RLM RM ID plus LMM in bracket IM plus ID, and phi Q will be LRM IQ plus LM in bracket IA IQ plus IQ divided by A square, where and phi m is the main flux binding. Flux will be phi m equal to LSM IM plus LLM IM ID and phi equal to LA IA plus LAM in bracket IA plus IQ upon A. So these are the flux with the four windings, 2 on stator, M and A, and D and Q winding on the typically on the rotor equivalent line. So for nonlinear saturation characteristic, it is better to define reduction ratio called A equal to under root LAM upon LMM, and the magnetizing inductance LMM and LAM along with the two axes are dependent on the resultant magnetizing current I mu. So I mu can be explained under root Im plus Id square, that is the current on the dialectric axis or main winding axis, and plus AIA plus IQ square under root of total line. So now developed torque will be T equal to minus P1 ID IQ minus phi Q ID equal to P1 LMM under root LM on LMM IAID minus IM IQ, and this is the torque, and we can have a speed derivative equation J upon P1 d omega R upon dt equal to T minus TL, and TL is a function of course maybe of speed, it depends on the load. So in case of single phase induction motor, we can say Vm equal to Vs and Va equal to Vs minus Vc. Here CVT upon C dVc upon dt equal to Ia. So a six order nonlinear model has been obtained. The variables are Im Ia, Id Iq, omega R Vc, while the source voltage Vs and the load torque equal to omega R as a function of theta r t constitute the two inputs, with the known Lm as a function of magnetizing current I mu and the LMM as a function of Im. Functions even the saturation current may be handled easily both during transient and steady state condition, and DQ model seems to be ideal for treating the transient of single phase induction motor, and cross coupling saturation may be gently accounted in DQ model, and the steady state is either obtained after solving the steady state 6th order taken by a numerical method or any given speed from 0 initial value. Now coming to single phase induction motor steady state analysis. So steady state analysis of single phase motor, the steady state performance reported in general on the no load and on load, the efficiency and power factor breakdown, lock rotor and torque and characteristic. To start with the auxiliary phase open and a genuine single phase winding high of induction motor steady state performance is investigated, then move to the capacitor motor to investigate both the starting and running steady state performance. So coming to steady state performance, the open auxiliary winding, the auxiliary winding open in the capacitor start or single phase induction motor and starting process is over. The direct and inverse and winding current component Im plus and Im minus are Im plus and minus equal to half in bracket Im plus JIE plus with the minus plus equal to half Im, and you can just see the here you have auxiliary winding current 0 I and main winding current with the supply voltage the M winding and with the phasor diagram with the voltage supply voltage and main winding current with the phi m angle, and where the of course the current in you have equal to Im plus equal to I minus equal to Im by 2, and you have equivalent circuit here of course steady state with the auxiliary main winding circuit which you already explained with the single winding, and of course the developed torque you can find out with the main winding T equal to 2 RR P1 upon omega 1 in bracket IRM square upon IS minus IRM square upon 2 minus S, Im equal to Vs upon RSM plus JM in bracket ZR plus upon 2 plus ZR minus by 2, and we have a steady state performance with open auxiliary winding. You can say the developed torque, and you have a torque characteristic in motoring for forward field as well as backward field, and typically with the starting torque 0 in generating region, motoring region. And then of course you have a typically now equivalent circuit with the split phase capacitor induction motor. We introduce the capacitor with the auxiliary winding here in the again to backward field and forward, and the two voltage are given here. Then you can go to the calculation of the split phase around capacitor Z plus equal to RSM plus JXM in bracket ARM plus RSM by S divided by RSM by S and JXM plus XRM, and ZM equal to refer to main winding delta theta JRM plus JXM minus J upon 2 A square XC and X equal to 1 upon omega 1 XC, and delta RSM equal to half RSA square minus RSM, and delta XM equal to half XA upon A square minus XM, and Z equal to RSM plus JXM plus the parallel component JXM in bracket JRM plus RM by 2 minus S RM by 2 minus S plus J XRM plus XM, and you can find out from equivalence it leads to V upon minus JX J by A by 2 and V S into 1 plus J by A2 with as a matrix form Z plus ZM minus ZM minus ZM and Z minus plus ZM as a multiplication. You can call it matrix Im plus and Im minus. So from this you can find out from matrix the solution for Im plus and Im minus from these expression, and then you can find out the developed torque T plus and Ta minus from these expression, and you can find out the net torque. Now coming to single phase induction motor tangent analysis. So single phase induction motor undergo tangent during starting, load perturbation or voltage X, and inverter fed in single phase in variable speed I tangent occur even during mechanical state during commutation mode. To investigate the tangent orthogonal state winding, the cross field or DQ model is in state coordination traditionally used, and in general the two windings are orthogonal but not identical. Only state coordinate may be used in DQ cross field of single phase induction machine. So first the DQ model variables are VDS equal to VST and VQS is VS minus VC T by A, and IDS equal to Im and IQS is IA into A, and where the equivalent circuit your auxiliary winding is dVC upon dt 1 upon C IQS upon A. You can see the typically the circuit of the DQ model where the motor equivalent rotor is put in D and Q, IDR and IQR with the currents, and typically the main and auxiliary winding are notation the VDS and VQS correspondingly with the current corresponding current IQS and IDS. And then you can go to DQ model with the state coordinate d phi ds equal to Vs minus RSM IDS and DQ del of EQS minus VS minus VC upon A into RS minus RS A square IQS, and d phi dr upon dt equal to IDM RRM minus omega R phi QR, and phi d phi QR upon dt IQR plus RRM plus omega R pi dr with these two terms of speed voltage. These are the four flux equation you can solve for forcing function as a supply voltage Vs, along with the typically where phi dm phi ds are explained here. LS Adam IDM plus phi dm, and phi dm equal to LM IDR plus IS LM IDM, and phi dr equal to LRM IDR plus IDM, and phi QR LSA square upon A square IQS plus phi QM, and phi QM equal to LM plus IQS plus IDR equal to LM IQM, and phi QR equal to LRM IQR plus phi QR. The magnetization inductance LM depends on both IDM and IQM when such is accounted for because of cross coupling effect, and the total flux phi m equal to the function of LM into IM, where IM is IDM square IQM plus IQM square, and phi m equal to phi dm square IQM. So once LM as a function of IM is known, it may be used for computation purposes with the previous computation step value provided the sampling time is n small m, and the motion equation is J upon P1 d omega r upon dt t minus TL, and d theta upon dt equal to omega r upon P, and where the torque is phi ds IQS minus phi ds r phi into P1. Now coming to starting tangent, during severe starting tangent, the main flux path saturation does not play a crucial role. So however, it is embedded in the model, it may be used so if desired. So you can see the speed with respect to the time, how it comes, and how the torque develop with the lot of torque pulsation because of the typically the unbalanced two-phase stator as well as the capacitor into the circuit, and typically total current and IDIQ and the capacitor voltage coming across. Now coming to the theoretical problems. Question 1, on which of the following symmetrical synchronous speed of linear induction motor use? The synchronous speed of linear induction motor depends upon the number of two poles and supply frequency. How can reverse the rotation of single phase split motor? To reverse the rotation of single phase motor, one can reverse the polarity of the starting winding or auxiliary winding, not both. In which direction does the saddle motor run? Direction of rotation is from the unshaded to the shaded portion of the motor. Since the phase angle between the shaded and shaded is small, the saddle pole motor produces only a small starting torque relative to the torque of full load. The question 4, in rotating magnetic field is produced by the current in two winding displaced by 90 degree. What is the principle is known? The principle of producing the rotating magnetic field is using two winding is known as a phase leading. The question 4, at which speed the torque developed by the single phase motor drops to 0. The torque developed by single phase motor drops to 0 at a speed slightly below synchronous speed. The question 6, the no load current of single phase induction motor is around typically around 70 to 80% of full load current. The power factor of single phase induction motor usually operate typically about 0.7 to 0.8. In auxiliary split motor, the number of turns in auxiliary and main winding is typically less than 1. Now coming to numerical problem. Question 1, a 240 volt 50 Hz 2-pole single phase induction motor operates at a slip of 4%, has a rotor resistance of 4 ohm. At its time to determine the effective resistance in the forward and backward field. So speed is given, synchronous speed you can calculate it with the pole 120 F by P, that 120 into 50 by 2, that is 3000. Slip is given as 0.04, so you can find out n equal to n into 1 minus s, so it comes 2880, and RF comes 0.5 R2 upon s 50 ohm, and RB equal to 0.5 R2 minus it comes 1 out of 1.02 ohm. Now question 2, 220 volt 6-pole 50 Hz single phase is single winding single phase induction motor has the following equivalent circuit: R1 3.1 ohm, X1 5.1 ohm, R2 1.6 ohm, and X2 equal to 2.1 ohm. Neglect the magnetizing current when the motor runs at 96% of the synchronous speed. Compute the ratio of the shaft torque to the forward wheel, and those slips are 1 minus 0.6 equal to 0.04. So since magnetizing current is neglected, Xm infinity, so T equal to 1 upon F I square R2 by 2s, and T equal to 1 upon S I 2 square R2 divided by 2 minus s, T total TFB minus T2, so R2 upon 2s I square bracket 1 upon s minus 1 upon 2 minus s, and TF upon T total is 1 upon s divided by 1 minus s minus 2 by s, so it comes 1.0208. Now question 3, in 6-pole 50 Hz single phase induction motor, the gross power absorbed by the forward and backward field are 160 watt and 20 watt respectively, and motor speed 150 rpm. If no load friction losses are 75 watt, find the shaft torque. So as given, PFG 160 and PFB 20. So PFG minus VD is 140, and the slippage, for this motor comes to typically about 0.05 by formula, and the developed power comes PD equal to 1 minus slip into PH, that comes 133 watt. Output power PD minus friction voltage, it comes 133 minus 75, 58 watt, and torque produced P omega 1 minus slip, so it comes 0.583 watt Newton meter. Question for a 4-pole 50 single phase induction motor has the effective stand resistance and 4 ohm referred to stator. The full load slip of the motor is 4.5%. The forward and backward component referred to the stator are 3 ampere and 4.5 ampere respectively. This is the full load torque. So PGF equal to IF I2 square R2 by 2 minus S. So it comes 3 square 4 upon 2 into 4 0.05, so 400 watt. PGB calculating it comes 20.176, and if load is PGB minus PGB, PGF minus PGB by omega, putting value it comes 2.41 Newton meter. Now coming to question 5, a single phase 230 volt 50 Hz 4-pole motor capacitor start motor has the following standstill impedance, and winding impedance is Zm equal to 6.4 J5 ohm, auxiliary winding is Z equal to 7.5, and it means the starting capacitor to be connected in series with the auxiliary winding 90 degree between the current of 2 in microfarad. So you can have a angle of main winding current Im plus pi by 2 should be angle of auxiliary winding current. So Z main is given 6.5 J5 ohm, and Z auxiliary 7.J5 ohm, and auxiliary 1 upon Xc. So putting the formula in the same with the winding current angles, we get here X equal to 13.51 and C comes to 37.54 microfarad. Coming to question 6, a 220 volt 6-pole 50 Hz single winding single phase induction motor has the following equivalent circuit parameter as referred to the stator: R1 equal to 3.1, X1 5.1, R2 equal to 1.6, and X2 equal to 2.1. Calculate the magnetizing current. Motor runs at 97% of synchronous speed. Compute the ratio of shaft torque to forward and backward TF upon TB. So slip here is given here 1 minus 0.73%, 0.03, and magnetizing current is neglected, Xm is infinity. You can have ZFB upon RFB, PGF upon PGB, and the value half I square R by S divided by half I square R2 by 2 minus S. So TFB upon PB comes 2 minus S upon S, and putting value it comes 65.7. Question 7, single phase 120 volt 60 Hz 4-pole capacitor run motor has the following equivalent circuit parameter: X1M equal to 2 ohm, RM1 is 1.5 ohm, R2M 1.5 ohm, and XA1A 2 ohm. So R1A 2.5, X2 2 ohm, XM 48 ohm, running capacitor C30 microfarad, and turns ratio is given here equal to N upon M. So determine the starting current and the starting torque of the motor at rated voltage. So calculating ZF equal to ZB at starting, S equal to 1, both will be equal. So it comes 1.2 at the angle of 54.85 ohm, and EF equal to EB equal to FA upon EB. So you can calculate the magnetizing IM main winding current V upon I Z1M plus ZB plus ZF. It comes 24.5 at the angle of minus 54 degree ampere, and I equal to V upon Z1 A minus JXC plus A square plus ZF plus Z2. Putting value it comes 1.421 at the at angle of 87.4 ampere, and the starting current is I is equal to 24.5 at the 54 minus 1.87.4. So it comes to your 23.4 minus 51.82 ampere. The starting torque is TS, the value 2I into IRF plus RB sin theta A minus theta m upon omega sum. The value it comes 0.318 Newton meter. So question 8, a 230 volt 60 Hz 6-pole single phase induction motor has the stator impedance 1.5 plus J3 ohm and its rotor impedance 2.3 ohm at standstill. The magnetizing reactance 50 ohm, and if rotational loss by 150 watt, the slip is 5%. Determine the efficiency and shaft torque of the motor. So slip is given 0.05, synchronous speed 4 pi f upon p, it comes 125.66 radian per second. Omega m equal to omega s minus 1s. Putting a value of slip, it comes 119.337, and the forward impedance ZF equal to 0.5. The XM 50 into in bracket 2 by 0.05 plus J divided 2.01 plus J3 plus 50, it comes 11.34 plus J 9.97 J ohm. and this ZB calculating from that, it comes similarly. You can get a sum of both as it is in ZF plus ZB. It comes 10.296 plus 14.394 I ohm, and you can find out IN equal to your voltage divided by this ZD. It comes 11.737 47 at the angle of 47.27 degree, and P in equal to 30 into 11.1 cos angle between the two 47.27. It comes 1831.73 watt, and PGF equal to IA square RA, that comes 61.85, and PGV equal to IA square RV, so it comes 62 watt, and PAG comes PGF minus PGV, it comes 1500 watt. And gross power developed PD equal to 1 minus H into PG, that comes 14.25, and output power, net output power PA equal to PA minus your rotational loss, so it comes 1275 watt. Efficiency comes output of one input 1275 divided by output of one input 69.6%, and shaft torque is your output power divided by the speed, it comes 10.68 ohm. So question 9, a 208 volt 50 Hz 4 pole single phase induction motor has R1 equal to 2.5 ohm, X1 2.0 ohm, R2 equal to 2.1 ohm, X2 equal to 2.6, and Xm equal to 42. The friction windage and core loss is 50 watt and slippage 4%. Determine the efficiency of torque of the motor. So slippage is 0.04, and omega is 4.5 by P, so 157.07. Omega m is 1 minus S, so it comes 150.79 radian per second. And you can calculate ZF from the formula, it comes 9.75. Similarly, ZB and ZIN will be ZF plus ZB, and IN will be your V upon ZD. You can calculate this 9.94 at the angle minus 50, and PN will be V in IN into cos phi, that comes 121258.05 watt. And you can calculate PGF, PGB, PGF 964 and 46 watt, and PAG equal to PGF minus PGB, that comes 917.15 watt, and gross power is D equal to 1 minus HPG, so it comes 880 watt, 0.47 watt, and net power output PO equal to this PD minus the friction voltage, so it's at typically at 30.47 watt, and efficiency output power is 66.0, and the shaft torque is your the output power by the speed is 5.507 Newton meter. Now come to unsolved problem. So similarly, we have unsolved problem with the answer. You can solve in the similar manner, and these are some of the books which used to develop this model. You can refer that, and thank you very much.